You know, in the history of science, there are these legendary problems, challenges that stand for centuries and basically define the limits of what we think is possible. I'm talking about things like squaring the circle or Fermat's last theorem. They're more than just puzzles. They're like these giant walls that tell us, nope, you can go no further. And today, we're going to look at a claim that someone may have just smashed right through one of the biggest walls of all. So, what if a problem that's been officially stamped as impossible for 2 whole centuries has actually been solved? Well, that's exactly what we're diving into today. We're exploring a brand new theorem that says one of math's great impossible problems might not be so impossible after all. And this is the beast at the heart of it all, the general ninth-degree polynomial equation. Yeah, it looks like a total mess, right? Ax to the ninth plus bx to the eighth and on and on. It might just look like a string of symbols, but for generations of mathematicians, finding one single exact formula to solve it has been a famously unconquerable quest. To really get why this is such a huge deal, we need to hop in a time machine. Because this isn't some new problem. It's a story about a mathematical wall that was built almost 200 years ago. Okay, just look at this timeline. It really shows you how long we've been stuck. Way back in the 1500s, mathematicians figured out exact formulas for equations all the way up to the 4th degree. But then, progress just hit a brick wall. In 1824, this brilliant mathematician, Niels Henrik Abel, proved that you couldn't find a general formula for the 5th degree or anything higher. And for almost 200 years, that was that. Game over. Until this new claim popped up in 2023. So what did Abel actually prove? This is the key. He showed there was no solution by radicals. Now, as you can see, that just means you can't write a universal formula using only the simple tools we all know: adding, subtracting, multiplying, dividing, and taking roots. It's kind of like he said, you can't build this skyscraper with only a hammer and nails. He didn't prove a solution was impossible, period. He just proved the standard toolkit wasn't up to the job. Okay, so why did those tools fail? Well, it all boils down to symmetry. Think of an equation's solutions like the corners of a shape. For the easy equations, those shapes are nice and predictable. But once you hit the 5th degree and go higher, the underlying patterns, what mathematicians call their Galois group, they just get wildly complex. The number of possibilities explodes, and you just can't pin them down with simple radicals. So mathematicians had to settle for close enough answers. And over time, everyone just sort of accepted that this was an absolute limit. But what happens when someone comes along who just refuses to accept that limit? Well, that brings us right into the present day, to a new challenge against this old accepted belief. And this quote pretty much perfectly captures the mindset of the mathematician behind all this, Professor Mourad Sultan Ezouidi. His entire work is driven by this idea. A limit is often just a frontier that's waiting for someone to cross it. Now, here's the really elegant part of his argument. He is not trying to prove Abel wrong. Not at all. He's saying Abel's theorem was totally correct, but incomplete because it was stuck using the math tools they had back in the 19th century. The argument is that the problem was never the equation itself, but the limited set of tools they were using to attack it. And this table just lays out the difference perfectly. On the left, you've got the classic approach, going back to Abel, which said it's impossible, so we'll have to settle for approximations. But over on the right, Ezouidi's theorem claims to deliver exact, 100% verifiable solutions by just rejecting that mathematical fatalism. It's a total flip, not just in the answer, but in the whole philosophy. All right, so how on earth does this new method supposedly work? Let's take a look at the big idea, the concept behind it, without getting completely lost in the formulas. Honestly, the best way to think about it is like peeling an onion. The method uses something called recursive transformations, which is really just a fancy way of saying you apply the same smart step over and over again. Each step uses the equation's own hidden structure to peel back another layer of complexity, revealing these hidden patterns. You just keep doing that until, eventually, the exact perfect solutions just pop out. And this is the whole point. We are not talking about a 99.9% accurate guess. The claim is for a 100% exact algebraic answer. It's about bringing these kinds of problems back to the world of perfect, verifiable precision and leaving the whole close enough era behind. Now, if, and it's a big if, this claim holds up to review from the rest of the mathematical community, the impact would be absolutely enormous. We're not just talking about solving one hard problem. We're talking about redefining what the word solved even means. What we're looking at is a massive philosophical shift. As you can see here, we could be moving from an age of mathematical fatalism, this belief that some problems are just plain unsolvable, to an age of mathematical possibility. The new idea would be that every single equation, no matter how ridiculously complex, actually contains the blueprint for its own solution hidden right inside. And really, that's the ultimate takeaway. This isn't just a clever trick for one specific problem. The ambition here is to literally redefine the boundaries of algebra, to prove that no polynomial is fundamentally beyond our reach. Which leaves us with a really fascinating final question. For 2 centuries, this problem was a symbol of impossibility. If a claim like this is proven true, and that wall really does come down, it just makes you wonder, doesn't it? What other impossible walls in science and math are just sitting there, waiting for someone to come along with a new perspective and show us they were never really walls at all?